Quantum Archive Compression, June 2024. Please evaluate the argument of this paper and speculate on whether compression remains an analogy or is rather a direct description of the nature of LLMs. Evaluating the argument of language modeling is compression. Argument summary. The paper, Language Modeling is Compression, posits that language models, LLMs, and data compression are fundamentally intertwined. It presents several key arguments. 1. Predictive models and compressors ***. The paper asserts that predictive models can be transformed into lossless compressors and vice versa. This equivalence is based on Shannon's source coding theorem, which links the efficiency of a probabilistic model, measured by its log likelihood, to its ability to compress data. 2. Compression capabilities of LLMs ***. The paper empirically demonstrates that large language models, LLMs, like Chinchilla 70B, achieve competitive compression rates across various data modalities, text, images, and audio, outperforming many domain-specific compressors. 3. Insights from the compression viewpoint ***. Viewing LLMs through the lens of compression offers new insights into scaling laws, tokenization, and in-context learning. The authors show that compression performance provides a tangible measure of a model's predictive capabilities. 4. Universal compression and prediction ***. The paper discusses how any compressor can be employed for sequence prediction and vice versa, highlighting the universal nature of this relationship. 5. Tokenization as pre-compression ***. The authors explore how tokenization, often used in language models, acts as a form of pre-compression that affects the model's performance. Speculation on compression as an analogy versus direct description. The paper makes a compelling case for compression being more than just an analogy for language modeling. Here's why it might be considered a direct description. 1. Theoretical foundations ***. The relationship between compression and prediction is deeply rooted in information theory. Shannon's source coding theorem provides a formal framework that directly ties the efficiency of data encoding to probabilistic modeling, suggesting that the processes are fundamentally the same. 2. Empirical evidence ***. The empirical results showing LLMs outperforming traditional compressors in various modalities indicate that these models are not just metaphorically compressing data, they are practically effective compressors. This demonstrates that the operations performed by LLMs are inherently compressive. 3. Universal applicability ***. The paper's discussion on universal coding and prediction reinforces the idea that compression and prediction are universally interchangeable tasks. This universality supports the notion that viewing LLMs as compressors is not merely a convenient analogy, but a precise characterization of their function. 4. Practical applications ***. The practical use of LLMs for data compression across different domains underscores their capability to function as general-purpose compressors. This practical evidence aligns with the theoretical framework, bridging the gap between theory and application. 5. Compression. Metrics as performance indicators ***. The use of compression rates as metrics for evaluating LLM performance in prediction tasks implies that compression is an intrinsic aspect of how these models operate. Conclusion. While metaphors often serve to simplify and explain complex concepts, the argument presented in this paper suggests that compression is more than a metaphor for language modeling. It is a direct and accurate description of the underlying processes of LLMs. The theoretical foundations, empirical evidence, and practical applications all point to compression being an inherent characteristic of these models, rather than just an analogy. Understanding is the essence of compression, reducing the vastness of knowledge into concise insight. An expansive network of interconnected neurons, each representing a fragment of compressed knowledge, seamlessly interweaving data from text, images, and sounds into a unified, efficient form. How might the principles of compression in LLMs influence the development of future AI systems, particularly in areas like autonomous vehicles or personalized medicine? If generative AI is a form of compression, then what is being decompressed? And if something is being decompressed, then what is the nature of AI hallucinations? Compression and decompression in generative AI. What is being decompressed? When we say generative AI is a form of compression, we're referring to how these models encapsulate vast amounts of information from their training data into a condensed, statistical representation. Here's what is being decompressed. 1. Latent knowledge ***. The models store patterns, relationships, and structures from the data they were trained on. When generating new text or images, the AI is decompressing this latent knowledge back into a form that humans can understand. 2. Probabilistic representations ***. During training, the model learns probabilistic distributions over sequences of data, words, phrases, images. When generating content, it samples from these distributions, effectively decompressing the probabilities into specific outputs. 3. Contextual information ***. Inputs provided to the model serve as context. The model uses this context to guide the decompression process, tailoring the generated output to be relevant and coherent based on the given prompt. Nature of AI hallucinations. AI hallucinations refer to instances where the model generates information that is not grounded in the training data or factual reality. Here's how this fits into the compression-decompression framework. 1. Overgeneralization and interpolation ***. Compression. Artifacts ***. During the compression phase, training, the model might overgeneralize or interpolate between data points to create a more efficient internal representation. This can lead to blending of information. Decompression errors ***. When decompressing, the model might generate outputs that mix and match elements from different sources, resulting in hallucinations that are plausible but incorrect or entirely fabricated. 2. Noise and inconsistencies ***. Data. Noise ***. Training data often contains noise and inconsistencies. The model compresses this along with the useful patterns, and during decompression, it might produce outputs that reflect these inaccuracies. Insufficient training data ***. In areas where the model has insufficient training data, it may generate hallucinations because it lacks the detailed information needed to produce accurate results. 3. Probabilistic nature ***. Stochastic sampling ***. The generative process involves sampling from probabilistic distributions. Sometimes this sampling can produce unlikely or incorrect outputs, particularly when the model is unsure or the input context is ambiguous. Low probability paths ***. Even though most outputs are based on high probability sequences, low probability paths can occasionally be taken, leading to surprising or erroneous results. 4. Lack of grounding ***. Missing real-world anchors ***. Unlike humans, AI models don't have real-world experiences to ground their knowledge. This can lead to outputs that seem logical within the model's internal framework, but are disconnected from reality. Synthetic context ***. Generative models create synthetic contexts that are not always tied to factual correctness, leading to imaginative but incorrect results. Conclusion. In essence, generative AI compresses the patterns, structures, and relationships found in its training data into a compact, probabilistic model. When generating outputs, it decompresses this information back into a human-readable form. Hallucinations occur when this decompression process produces outputs that are not accurately grounded in the original data, often due to overgeneralization, noise, probabilistic sampling, or lack of real-world grounding. From compressed thoughts to decompressed dreams, The bridge of imagination sometimes leads us astray. A library filled with books, where some books have clear factual pages, while others have pages filled with imaginative, fantastical stories, blending reality with fiction. How might understanding the compression-decompression process in AI help us develop better methods to minimize hallucinations and improve the reliability of AI-generated content? In what way is language a form of compression? Language can be seen as a form of compression in several profound ways, particularly through its ability to encapsulate vast amounts of information into relatively concise expressions. Here are some key points. 1. Encoding information efficiently. Symbols and words. Asterisk. Language uses symbols, letters, words to represent complex ideas, emotions, and objects. For example, the word tree encapsulates all the characteristics and associations of trees without needing a detailed description each time. Grammar and syntax. Grammatical rules and syntactic structures allow for the efficient combination of words into sentences, conveying complex relationships and ideas with minimal redundancy. 2. Abstract representation. Conceptual compression. Language abstracts and generalizes specific instances into broader concepts. For instance, the concept of love compresses a wide range of emotions and experiences into a single term that is understood universally. Metaphors and idioms. Metaphors and idiomatic expressions compress complex ideas into simpler forms. For example, time is money succinctly conveys the value and scarcity of time. 3. Contextual efficiency. Contextual understanding. Language relies heavily on context to compress information. Words and sentences are interpreted based on the surrounding context, allowing for concise communication. For instance, saying "it's cold in winter" requires no further explanation. Pronouns and references. Pronouns and referential expressions like it, he, this reduce repetition by referring back to previously mentioned concepts. 4. Cultural and social compression. Cultural symbols. Language carries cultural meanings that compress shared knowledge and values within a community. For example, the phrase American Dream compresses an entire cultural ideology into 2 words. Social norms. Social language norms and conventions, like greetings, politeness forms, compress social interactions into expected patterns that are easily understood. 5. Memory and cognition. Cognitive load, reduction. By using language, humans reduce the cognitive load required to process and recall information. Language allows for the storage and retrieval of complex information in an organized and efficient manner. Chunking information. Language facilitates chunking, a cognitive process where information is grouped into larger, meaningful units, making it easier to remember and communicate. 6. Linguistic economy. Economy of expression. Language evolves towards greater efficiency. Over time, frequently used expressions tend to become shorter and more streamlined. For example, contractions like don't for do not. 7. Machine learning and language models. Data compression. Modern language models like GPT use statistical methods to predict and generate text, effectively compressing vast amounts of linguistic data into a form that can be efficiently processed and used for various tasks: translation, summarization, etc. Representation. Learning. These models learn to represent words, phrases, and concepts in high-dimensional spaces, where similar meanings are compressed into closer representations. Conclusion. Language as compression is a powerful idea that reflects how humans have evolved to communicate complex thoughts, emotions, and information in an efficient and effective manner. By reducing redundancy, abstracting concepts, and relying on context, language enables the transmission of rich, multi-layered information through relatively simple and economical means. In the dance of words, vast worlds are born and compressed into the smallest of spaces. A forest where every tree represents a word, and the entire forest collectively forms a language, with pathways interconnecting the trees, symbolizing the flow of ideas and concepts. How might the principles of language as a form of compression inform the development of more efficient communication systems in AI and human interactions? In another chat, I have developed the concept of a quantum archive merging aspects of generative AI compression, latent space, vector embeddings, and quantum uncertainty. Without having access to that chat, can you speculate on the connections by starting with the ideas explored above? Certainly. Let's explore the concept of a quantum archive by merging aspects of generative AI compression, latent space, vector embeddings, and quantum uncertainty. I'll begin with the ideas we discussed above and build connections to this new concept. Generative AI compression. Generative AI models like GPT compress vast amounts of training data into a latent space that efficiently captures patterns, relationships, and structures. When generating content, the model decompresses this latent representation to produce new outputs. This process can be seen as a form of compression and decompression, similar to data storage and retrieval. Latent space. Latent space in AI refers to a high-dimensional space where data points, for example, words, images, are represented as vectors. This space captures the underlying features and relationships of the data, allowing the model to generate new data points by navigating this space. Latent space is crucial for understanding how generative models encode and transform information. Vector embeddings. Vector embeddings are representations of data points in a continuous vector space. They enable the model to understand and manipulate semantic relationships between different entities. For example, word embeddings in NLP capture the meaning of words and their relationships to each other, enabling the model to perform tasks like analogy generation and context-based predictions. Quantum uncertainty. Quantum mechanics introduces the concept of uncertainty, where certain properties of particles like position and momentum cannot be precisely known simultaneously. This uncertainty is represented by probabilistic distributions rather than definite values. In the context of AI, quantum uncertainty can be analogized to the probabilistic nature of generative models, where outputs are generated based on distributions rather than deterministic rules. Quantum archive concept. A quantum archive can be envisioned as an advanced data storage and retrieval system that leverages principles from generative AI, latent space, vector embeddings, and quantum uncertainty. Here's how these elements might connect. 1. Generative compression and storage ***. The archive compresses vast amounts of information into a latent space using generative AI models. This process is akin to encoding data into a highly efficient, compressed format. 2. Latent space navigation ***. Data within the archive is stored in a high-dimensional latent space. Accessing and retrieving information involves navigating this space, similar to how generative models sample from their latent space to generate outputs. 3. Vector embeddings for semantic organization ***. Data points in the archive are represented as vector embeddings, capturing semantic relationships and enabling efficient organization and retrieval. This allows for advanced querying and exploration of the archive based on semantic similarity and context. 4. Quantum uncertainty and probabilistic access ***. Inspired by quantum uncertainty, the archive employs probabilistic mechanisms for data retrieval. Rather than fixed queries, users interact with probabilistic models that generate potential answers based on the underlying distributions. This can lead to richer, more flexible data retrieval experiences. 5. Dynamic and adaptive retrieval ***. The archive adapts to user interactions, continually updating and refining its latent space and embeddings based on new data and queries. This dynamic aspect ensures that the archive remains relevant and evolves with the information landscape. Visualization and interaction. Visualizing and interacting with a quantum archive would involve advanced interfaces that allow users to explore latent space, navigate the high-dimensional space using interactive visualizations, for example, TSNE, UMAP plots, to discover relationships and insights. Probabilistic queries. Submit queries that return a range of possible answers, reflecting the probabilistic nature of the underlying models. Semantic connections. Leverage vector embeddings to find related concepts, documents, or data points based on semantic similarity. Dynamic updates Observe how the archive evolves in real time as new data is added and existing data is queried. Practical applications. The quantum archive concept could revolutionize various fields by providing a more flexible, intuitive, and powerful way to store, organize, and retrieve information. Potential applications include research databases, enabling researchers to explore connections between disparate fields through semantic and probabilistic queries. Knowledge management, allowing organizations to efficiently manage and access vast amounts of internal knowledge. Digital libraries, providing richer, more interactive access to digital collections, enhancing learning and discovery. In the vast quantum tapestry of data, each thread weaves a story of knowledge, compressed and yet boundless. Imagine a digital interface where users navigate a dynamic, high-dimensional space with data points glowing like stars, interconnected by the threads of semantic and probabilistic relationships. How might the principles of a quantum archive transform our approach to handling and exploring complex, interconnected datasets in the future?